Hello everyone. Today I will be presenting our ECG project which we designed as a part of our EW2 course under the mentorship of Dr. Aarti and Dr. Spandan Roy. I am Gautam Gandhi from IIIT Hyderabad and this project was completed in collaboration with my teammate Devansh Vajpayee. In this video, I'll explain the theory behind ECG signals, our circuit design approach, stage-wise analysis and demonstrate the working prototype. Let's start with some basic theory. An ECG records the electrical activity of the heart. When cardiac cells undergo polarization and depolarization, they generate small electrical signals in the millivolt range. We aim to detect and visualize these signals with our circuit. Our main objectives were to design a circuit that accurately measures the heart's electrical activity using basic analog components and to calculate the heartbeat of a person using this data. The challenge here is that these signals are very small, only in the millivolt range, and are easily overwhelmed by noise. To tackle these challenges, our circuit design follows a systematic approach with multiple stages. First, we need to amplify the weak signals. Then, we need to filter out various noise components while preserving the frequency range of interest for ECGs, which is typically between 0.5 Hz and 150 Hz. Finally, we need to condition the signal for display and heart rate calculation. The first stage of our circuit is the instrumentation amplifier as shown here. We are using three US741 op-amps configured in a classic instrumentation amplifier topology. The advantage of this configuration is that we can achieve high gain with excellent common mode rejection, which is crucial for eliminating noise that appears on both input electrodes. This stage amplifies the differential signal between the two electrodes while rejecting common mode noise. After amplification, our signal passes through a high-pass filter. This filter removes baseline bonder and very low frequency artifacts. The cutoff frequency is calculated approximately as 0.48 Hz. This means that frequencies below 0.48 Hz will get attenuated, while frequencies higher than this will pass through. Following this high-pass filter, we have an active low-pass filter. This filter attenuates high-frequency noise above 398 Hz. We choose a cutoff higher than the typical ECG bandwidth to ensure that we preserve all relevant cardiac signals. Next comes the active notch filter, which is critical for rejecting 50 Hz power line interference. The notch frequency is tuned close to 50 Hz to eliminate mains hum, which is the most common source of noise in ECG recordings. One notch filter wasn't enough to completely eliminate power line interference, so we implemented a second notch filter using a twin T configuration. This active twin T filter provides deeper attenuation at 50 Hz. We calculated the notch frequency to be approximately 48.3 Hz. Having two notch filters in cascade significantly improves the rejection of 50 Hz noise, potentially providing up to 50 decibels of attenuation at this frequency. The twin T configuration offers a sharper notch than a single stage filter. The final stage of our circuit is the output buffer and level shifter. This stage serves a critical function. It limits the output voltage range to 0 to 5 volts and centers the signal at 2.5 volts. This signal conditioning is essential for interfacing it with the Arduino's analog to digital converter, which requires a signal within the 0 to 5 volts range. This stage ensures our ECG signal can be properly digitized by the Arduino for heart rate calculation. Now, let's have a look at the results. This is the ECG waveform captured by our circuit. You can clearly see the characteristic P wave, QRS complex and T wave patterns that represent a single cardiac cycle. The output voltage range is between 2.2 volts and 3 volts after the signal conditioning stage. As you can see in this output, our circuit effectively eliminates the 50 Hz noise while preserving the ECG signal's integrity. The frequency response analysis on the oscilloscope confirms the functioning of our 400 Hz low pass filter and 50 Hz notch filters. There are a total of 3 electrodes needed to capture the electrical activity of the heart. The first electrode is placed under the right clavicle near the right shoulder, within the ribcage frame, and the second electrode is placed under the left clavicle near the left shoulder within the ribcage. The third electrode acts as a reference electrode and is placed on the left side below the pectoral muscles, lower edge on left ribcage. Beyond displaying the ECG waveform, we also implemented heart rate calculation using an Arduino Uno. The Arduino samples the conditioned signal, detects R peaks using a threshold algorithm, and calculates the heart rate based on the time between peaks. This heart rate is updated every 10 seconds and displayed on an OLED screen, giving real-time feedback about the subject's cardiac activity. In conclusion, we successfully designed and implemented an ECG circuit using basic analog components. The system effectively captures, amplifies, and filters cardiac signals, allowing for both waveform visualization and heart rate calculation. This project demonstrates the application of analog electronic concepts in biomedical instrumentation and provides a foundation for understanding more complex medical devices. Thank you for watching.